Okay, so we've been talking about significance tests, but significance tests really can't tell you whether, like when you find a result significant, that doesn't mean that you can tell that it's a causal result. For example, in this experiment we're engaged in, between the online section and the in-person section, we found in the first year we did it, which was last year, or even the first semester, even we started a year and a half ago, we got some astounding results in Stat 100. We got tremendously significant, statistically significant results that the online class on every exam was doing better than the in-person class. And overall, it was highly significant. It was less than 1%, the chance that we would see such results just by the luck of the draw. Now, we got different results in Stat 200, the class you're in now, so I'm not going to talk about that now. I'm just talking about, let's just do this. We had amazingly significant results. Now, you remember, everything was, as you know, everything's the same. You get the same exams, the same homework, the same lectures. They're just either delivered in person or online. Everything's the same. Those of you who are in Stat 100 know that it was the same course. We grade everything together. There's no difference except for the lecture delivery, whether you can see it online or in person. So we were thinking, okay, does this mean you get unbelievably significant results? That means we reject the null, right? That the difference we see is just due to chance, right? We reject that overwhelmingly. We know it's just very unlikely that what we're seeing is due to accidental random chance differences. It's due to some systematic difference, but can you say, like a lot of people just conclude and say, okay, that means online is better. Hands down, we've got overwhelmingly significant results. What do you guys think? Anybody want to comment on that? Can we conclude that it's the online delivery system that's making that difference? Yes, go ahead.
We need to know why people chose to take online section and why people chose to take in-class section.
Okay, so what he said is you can't yet because of the way the people themselves chose to be in online or in person. They were not randomly assigned. That's the key difference. And he said, if they chose, that means that everything is not the same. Everything is not the same. The people themselves might be different. And so we have to look at what is different about those online people versus the in-class people. So we did. That's called a confounder, a difference between the two groups that might be the true cause of why they're getting higher exam scores. We can't just automatically conclude, as so many do, even when I present these findings to trained people, they just automatically, just because we want to see a reason, we see such a big difference, we think, oh, it must be due to that's the difference because everything else is the same. But we forget we did not randomly assign them to treatment and control. So that's what this lecture is about. This lecture is about why randomization would allow us to conclude causation, and then what to do in a situation like the situation you're in right now, where no one wants to be randomly assigned right now. They want to choose. How can we determine whether it's the online or the in-person, or how can we tease out what's causing it in the absence of the online, in the absence of a randomized experiment? Okay, so that's a lot of things that we're going to begin to talk about right now, and we will be talking about and examining in many different ways through modeling situations, through creating these models, through many different ways throughout the semester, because people, if we want to change something and help people and tell you guys which would benefit you more, which people would benefit by the online, which people would benefit by the in-person, which is our goal, If we want to change something and improve conditions, that's causation. We can't just see association, we can't just make predictions. We want to affect change and make education better, or make the world a better place. If you ever care about that, making any changes, you have to figure out what the cause is. So that's what this whole course is really about. It started with Stat 100. That's my interest. And I think statistics is a way to do it. So let's dive in here. So what I said was significance tests do not distinguish between association and causation. They don't. You do the same exact significance test for experimental and observational data. Doesn't matter if the people chose themselves or they were assigned randomly or non-randomly. You do the same significance test. You get those same p-values and you get those same conclusions. In other words, we compute the same test stats, like the same z, t, whatever test statistic, and p-values to test the null hypothesis of no difference between various groups, whether or not group membership was chosen by the subjects themselves, or fate, or non-random assignment, or randomly assigned by the experiment. Why is that? Because all we're really doing when we're doing these significance tests is testing whether some signal that we observe, some difference we observe, is whether there's a signal at all, whether we can discern the signal amidst a bunch of noise. We're trying to separate, there's a lot of random noisy stuff, and we just want to see if there's any signal coming through amidst that noise. And that's all we're doing, not where the signal came from, just whether there is some signal at all, there's some difference at all. It's not due to random variation, but it doesn't tell us where that signal came from. Okay? So, that's super important because even though people learn this in stats classes, they can't help it because I guess because everybody wants to, find a reason. We naturally do that, and so we mix up. That's why I concentrated on it so much, how to get at causation, because you can't just do it from the p-values. All right, so the significance test is a statistical check to see if it's likely that there's any systematic connection at all between the treatment, the explanatory variable, and the response. It's not a check to distinguish between different types of connections. You can't say, you see two things connected. All it's saying is significance test, if you reject the null, is you say you have strong enough evidence to see some systematic connection between, let's say, A and B. It doesn't say whether A causes B, B causes A, or some third variable, C, is causing both of them. And that third variable is called a confounder. All right. So now you say, okay, if a statistical test doesn't distinguish between, a causation, what does? What can we do? And basically, what really allows you to specify a genuine causal relationship is random assignment, okay, of the explanatory variables. When you randomly assign people, it does two things. First, it eliminates human bias. When people try to match the groups up to be as alike as possible, they invariably introduce bias. And it also allows you to model the random differences. If you're randomly assigned, then everything in the beginning, before you administer the treatment, and the only thing that's different between the two groups at the start, all the differences are due to accidental differences, random differences that can be modeled by a probability model. Basically, they allow us to use our statistical methods so that when we reject the null hypothesis, assuming it's just random variation, the only thing that's left, we're saying, okay, it's very unlikely to be due to random variation. Well, the only thing that's left besides that is the treatment, because everything else was the same except for the accidental random variation. So it allows us to use our statistical tests to conclude causation. We can still do these tests on observational data. We do it all the time, but we can't then conclude causation. We can't say it's the difference that that difference that's causing it. Could be some other difference between the two groups, maybe because they chose, maybe better students chose to be in the online course, and it has nothing to do with the method of delivery. Okay, so in the absence of a randomized experiment, is there any type of statistical analysis that will allow us to figure out causation? And that's what this course is going to be about, trying to do that. But before we answer that question, we first have to really remember what exactly it is about randomized experiments that allow us to conclude causation. And then see if we can somehow get at that, whatever that is, without randomized experiment. How can we do our best to get at that? What is it about the randomized experiments that allows us to conclude causation? So, why do randomized experiments allow us to conclude causation? Okay, well, because the first reason I say is because it eliminates systematic bias that would be introduced if we did it any other way, right? When subjects are assigned to treatment and control by this objective chance procedure, like a flip of a coin, that we know the rule, that then the rules of chance are going to govern that procedure, and we can analyze those rules of chance, right? We know mathematically we can predict what types of differences we'd be likely to see. And that's exactly what we do with the null hypothesis and our test statistic, all right? And it eliminates the systematic differences between the groups that we have no way of evaluating or assessing the chance of them occurring. So, and another thing is that within, well, think about it, within random error, a systematic objective chance procedure is going to balance the two groups. Think of one group here as the treatment group, here, and another group as the control group. Remember, we want them as alike as possible on all characteristics. Now, we could try to do that, but remember, there could be a lot of hidden characteristics that we don't identify. A random chance procedure will make sure they're balanced on all the characteristics, not just the ones that the researcher identifies as important. And so then let's say, so we randomly assign them to the two groups. And if there's a large enough sample size, then the accidental differences the random differences will average out the accidental differences. Think of flipping a coin. Let's say you only have 4 subjects. Think of flipping a coin four times. You could get 100% heads. You could get 0% heads. But if you've easily, but let's say you flipped it 400 times. You're going to get closer and closer to balance, to 50% heads and tails, right? If you flipped a coin 400 times and you got all heads, you'd know for sure that was a fake coin, right? If you did it 4 times, you wouldn't know for sure at all, right? You have to flip it more times. And the more times you flip it, the more subjects you have, that the law of averages says that, you know, those random differences are going to get averaged out and you're going to have a balanced experiment. And so there's balance to begin with. So now let's just think of our ongoing experiment, that Stat 100 experiment we're talking about, where you have the people who are in the, let's just say, well, let's call the in-person group the control group because it's what we've been doing all along, and now we introduce this online, which is like a treatment, okay? You can call either one the treatment and control. We're just comparing two groups. So now, if we randomly assigned those thousands of people, there's like 2,000 people, into these two groups, they're going to balance out. You're not going to we don't have to worry about why they chose different types of people choose online than choose in person. And then on all the characteristics, even ones we don't even think are important, are going to be balanced. All right, at the start, before we even teach them. This is at the start. Then they either get the online or the in-person instruction, and then at the end, this is some measure of, this is the response, which is like their exam scores or the outcomes, any measures of learning outcomes we have. And then if the scales are tipped like this, then we can say, we can conclude that the online, if this was the online, the delivery system actually works better because everything else is the same. But if they choose themselves, well, we thought they might be better students who are more mathematically confident when they come their first semester coming here, freshmen, they might be afraid of an online course. And sure enough, that I'm not sure if that's the reason, but the ACT scores, especially the math ACT scores of the online group, were well above those, about a standard deviation above, hugely above the other one. And so that would explain maybe why that happened at the end. So if they're very unbalanced to begin with, how can you tell whether this unbalance at the end is due to the online, the actual method of delivery that we're trying to test, or whether it's due to some other difference like ACT? And that was only one difference. There's lots of other differences. So randomization is best. All right. Now, let's just do an experiment on randomization. So back to your iClickers, okay? And, all right, so on the screen, you are going to see, just very briefly, a set of numbers. Just randomly choose one on your iClicker, okay? So let's just do that. All right, just do it. Oh, I didn't start it soon enough. Just random, fastest, just choose one, okay? All right, and now let's see what you chose. Whoops, what did I do here? Okay, I wanted to get the result. I blew it. All right, so I go back here. Is there a way to get those results, David? I just blew that. I wanted to get a graph of the results. I've never done it as an iClicker before. Okay, raise your hands. If you chose one, I just want to see what happened. Raise your hands. 1, 2, 3, 4, 5. If you chose, or 6. If you chose 3, raise your hands. You see? Look at the difference. Look around. If you chose 2, raise your hand. Or 4. Okay, this happens every time that overwhelmingly 3 is by far the most popular choice. Usually about 75% of the people choose 3 rather than you'd expect what if it was truly random, meaning some objective chance procedure. Like if you reached into a hat, each one of you had a spinner and spun, wouldn't you expect to have an even distribution? 25, 25, it's never that way. Again, how many people choose 1? Raise your hand. So look at this, look around guys. Now how many people chose 3? Raise your hands. Hugely different. Okay, and 4? Raise your hand, very few again, and 2. Okay, so it usually is the middle numbers more and 3 more than 2. And 1 and 4 are the least chosen. So sorry I screwed up the graph, but you got the idea. So what do I mean? That's a very important illustration of what? Of how these differences, these accidental, basically that you guys have a systematic preference, a bias, human bias you weren't even aware of. Usually when we talk about bias, you think about sexual, racial bias, biases that you don't think about a bias against the number 1 and for the number 3 or something like that. So, but basically we're hardwired to have systematic preferences. That's just how humans are. And so there are many preferences. This will play out in our choices if humans are involved in how to assign people to treatment and control. Then we can't explain, we don't know these biases. And we know we have them, that's all for sure. We wouldn't be able to operate as human beings if we didn't have them. So that's just the way it is. So this is a way to protect ourselves against that bias and the randomization. And also another illustration, what else I wanted to illustrate, more importantly maybe even, is the way that we use the word randomly in everyday language. In everyday language, we use it to mean what? Just haphazardly. I just random this or random that. That's extreme. That's very different than how we use it in statistics. In statistics, what we mean by random is a planned introduction of chance, so that you can, for example, we could say, okay, I want each one of those to have an equal probability of being chosen, so we put all those 4 tickets, numbers in a box, shake them up, and choose one. I was going to say 4-sided die, but you can't have a 4-sided die, can you? Right? So, but, or a spinner. What?
It's like a pyramid.
Can you do it with 4 equal sides? Oh, they have 4-sided? Equal? I don't think so.
Area-wise, you can probably
If you take an equilateral triangle.
Yeah.
Oh, okay.
How much damage a dagger does for like 30 years?
In role-playing games,
I don't play role-playing games. I haven't seen this. Okay, so you have the 4-sided die. All right. So then there's another example. Right. So you wouldn't be more likely to get one number or another. Good. Thanks. All right. So that's the idea there. So now let's go back to the document camera. Okay. So now, but as I said before, what if you have a small sample? So randomized studies eliminate confounders as long as the sample size is big enough for those accidental differences to average out. But with small samples, what researchers do is they block subjects first into relatively homogeneous groups, and then flip a coin to decide, or use some objective chance procedure to decide who's in treatment and who's in control. So that reduces the accidental, it's a way to reduce accidental differences in small studies. So here's what I mean. And let's look at this. And this is a real life example, a blocking example. I wrote this notebook the first time I taught Stat 200, and I was hand grading because I didn't have time to put all the homework into computer systems. So partway through the semester, I started to be able to do that, and I said, suppose I wanted to see whether computer graded homework helps students do better on Stat 200 exams compared to the current hand-graded homework. All right? And let's say there are only 36 students in the class. The class was small, okay? And 18 of them had A averages so far on the exams, and 18 of them had B averages. With only 36 students, that's pretty small sample size, random assignment into computer and hand-graded groups could result in large accidental differences. For example, and here's the example. So if I didn't block, if I just said, okay, I have 36 students, half of them have A's and half of them have B's so far, right? And so let's say I just put their names on tickets in a box. I have 36 tickets. I shake them up, shake up that box, so they're all random. And then I take out the first 18, divide them into 2 groups randomly. Take out 18, leave 18 in the box, right? And then I open up see who their names are, and I get this. 13 people have A's so far in the computer graded, and only 5 B's, and in the hand graded, it's the opposite. That's very unbalanced. The problem would be if it's like that, that would be, I wouldn't be able to, we'd have very unbalanced groups to begin with. Then if I got this result at the end, I wouldn't know, whether it was due to I just wouldn't be able to tell. That's confounding, right? So, how does blocking help? Well, and why doesn't it introduce human bias? Well, there's bias at this point. I'll block. I know that whether past exam, getting an A on your past exam is going to predict A better on your next exam. So I know this is pretty obvious. So I want to control for that. I want to eliminate that confounder. And so what do? I block into 2 groups, the A group and the B group. And then, here I have 18 people, and then I shake that box up and I randomly divide it into 2 groups and randomly choose 18 people, let's say, to be in this group, 9 people to be in this group, and 9 to be in that. That ensures an even balance between the two groups, and then I'll do the same with the Bs. So I didn't look at who they are, so the final assignment is random, and what it does is just, it makes things more even. It balances out the groups. So that's what's done all the time in randomized experiments, even in large randomized experiments, if there's some particular feature that they want exactly balanced. Okay, so that is the idea there. Any questions so far? And so, so people say, well, is it always better to block first? Yes, it's always better to block first and block not just on one. You could block on other characteristics you think are important, but as the experiment becomes large, it's just pretty much unnecessary. So with small experiments, it's very important. So it's always better to block first. And then at the final step, randomize. Especially in small studies to protect against big accidental differences that will disappear with a large study. All right, so that's the idea. Any questions so far on that? Okay. Now we've been talking, so randomization is ideal, but would you guys want to be randomly assigned to the, I would love it if I could do it. I could find out, if I could randomly assign all the students to either the online or the in-person class, it would be amazing. I could determine what was going on. Right now it's a lot of work. But who's going to consent to that? Most students would not want that, would not want to be randomly assigned. You would? Are you going to raise your hand for a question or just saying you would do it? What?
I would do it.
How many people would do it? Maybe we could, how many people in this, we should do an iClicker question. Just, well, I can see by hands. How many people would consent to be randomly assigned to one or the other? Just raise your hand high. How many people would not? Yeah. You want to have a choice in how you learn. And I think that's really important to have a choice in how you learn. I think you learn better when you do have the choice. But it's a terrible way to figure out which way works better. It's a wonderful way once we decide, when we're not in the middle of an experiment, it's wonderful to allow choice in education. Basically, that's why I started this whole online thing, to give people a choice. But it's a terrible way to figure out what's going on. But we still can, and we're doing it. And how do we do that? So that's what this is about. What do we have to, do? So the main problem with observational studies and non-random assignment, non-random experiments, both, is just the non-randomness. Is confounding, okay? That's the main problem. So we talked a little bit about confounding. I just trying to find my glasses here. I realized I need them here. Hold up. See if I have them. Okay, so all right. So with observational studies and non-random, the subjects themselves or some other non-random cause decides group membership. So there's bound to be systematic differences between the groups besides the treatment. Okay, since the groups aren't balanced to begin with, it's difficult to conclude causation. So what are we going to do? So what we're going to do is something very similar to blocking, but we're going to do it, we can't do it before the assignment, right? Because in observational studies, the subjects themselves are choosing. We'll do it afterwards in analyzing the data. It's called stratification. So let's see how this works. So observational studies can only show association. The two things are associated. It's really hard to show causation because the groups are different in other ways besides random. They're necessarily different unless they were randomly assigned. There's going to be other differences, non-random differences. So let's think about this. So you see some association. Let's say this is the situation we were in at with the online course last semester, or 3 semesters ago in Stat 100. We saw this overwhelming difference. And by the way, it held up for the following year as well. And so we're left with this. Did the treatment cause the response? With the computer grading or with the online, we can stick with the computer grading example. Did the computer grading somehow cause the students to have better grades? Why? And this is computer grading on the homework, not on the exams. So why would computer grading? So I thought, well, maybe immediate feedback was helpful to the students. They could get the results right then. It's like immediate feedback is very important in learning. It's touching a stove. You get that immediate feedback. It's hot. You learn. So I thought maybe that is causing the better grades on the exams where they weren't computer graded. They were just learning better. Or because they chose themselves, there could be some possible, there's a systematic difference between people who choose the computer grading and people who choose the hand grading, right? There could be a systematic difference between them. And that's really what's causing the better grades. And that's linked or causing them also, or linked to, the computer grading. CG is computer grading. If you'll forget, probably. It's the other example. Computer grading. Okay, so what could that be? It could be the better students to begin with. The ones who are getting A's are choosing the computer grading. They might choose it, okay? So how can we tell which is which? So what we can do is we can stratify. And that is, let's say there were better students choosing the, more A students were choosing the computer grading. Well, then what can we do? So this is, so we're going to do exactly what we did before, but we do it after the experiment. We call it is finished when we look at the results, and it's called stratification. It plays the same role as blocking does in experiments as for, it plays that same role for observational studies. So what can we do? So we're now on page 18. So we're going to pretend we're going to do the same exact example, this time pretending it was an observational study. All right? So suppose the 36 students in Stat 200 were allowed to choose themselves instead of by random assignment to be in computer or hand-graded homework group. So let's just say that we got that 13 A students and 5 B students chose the hand-graded. Wait a minute, 13 A students, 5 B chose the computer-graded. Well, 5 A's and 13 B's chose the hand. So it looks like this, all right? Then, of course, the scales would be tipped the same way in favor of the computer grading. So what we can do is we want to basically compare apples to apples, right? These are unbalanced scales. So what we want to do is compare the A students to the A students. So there we're comparing likes to likes. and then the B students to the B students. And what first jumps out at you probably is, wait a minute, there's a lot more A students. Isn't that going to mix up the results? Well, remember, what we're comparing is going to be the average exam scores. The average, right? So the average of the 5 A students and the average of the 13 B. There's going to be a lot of random error because there's only 5 of them here, right? There's going to be, so it means that you have to have bigger sample sizes, because that's pretty small, but that's a better way of doing it even with 5 students than just mixing them. Look, than just looking at these, the average of all 18 here and the average compared to that. Okay, so that's the idea there. And then the problem is you really do need a bigger sample size, and especially if you think about, what if we thought that income was also a confounder? Maybe high-income students might be more likely to choose computer grading. Maybe they have more access to computers, and they might also just do well on exams because they've had better background. And how could we stratify to account for both confounding variables? So we'd have to then break each of the subgroups, the A's and the B's, into more subgroups by income. And let's say we did 3 categories of income, high, low, and middle. Well, that means that we have 6 groups compared to 6 groups. And so if you just think about it, we'd have a high, a middle, and a low for each of them. 1, 2, 3, 1, 2, 3. So we're going to have 6 groups. So that's high, mid, and low. Excuse my spelling here. High, mid, and low. All right, so we want to compare A students from rich backgrounds to each other, and then A students from middle class backgrounds to each other, et cetera, and do the same all along. Well, that means we have 6 of these groups, and look at it, we only have 5 A students. So either one of the categories has, at best, can have just 1 person, which is great and easily could result in 0 people. So basically, you can't do that unless you have huge sample size. So one way to deal with this problem is another way to do the equivalent of stratification or something very similar is by modeling, creating a model that includes the confounders as explanatory variables in your model. And so they're called, you would call them covariates, that allows you to basically do this even when you don't have a large enough sample size to do it exactly this way. Okay? So we're going to be talking about modeling very shortly and creating linear models, not only to make predictions, because linear model is used all the time to make predictions, but also to tease out causation, to figure out what's causing what, you know. So that's what we're going to be doing. And now let's just make sure, so here, first of all, so with observational study, this is key right here, you need a much bigger sample size than with experimental data, because each time you stratify a possible confounder, that group gets, the comparison groups get smaller and smaller. All right, so now let's turn the page here. And this is an example that was in the Stat 100 notebook as well. And it's a problem, it's a classic clear-cut case of confounding that will help you, I believe, in learning by examples, that will help hopefully anchor in your brain what a confounder is. Okay, so this is I think it's really helpful. I think all of you should do this. You think of extreme cases, extreme examples on your own to help you remember things. Because, so this isn't one of those. All right, suppose observational studies showed that people who carry lighters have a higher rate of lung cancer. So now the two are linked. So you can think of lighters as the treatment, lung cancer as the response, even though it's a bad response, right? So lighters is the treatment, lung cancer is the response, and on first, you can't randomly assign, well, I guess you could randomly assign people to carry lighters, but let's say, or not lighters, but we didn't. So there's lighters and lung cancer. And of course, people first think it must be the lighters causing the lung cancer, right? And your next step would think, well, if it is the lighters, is there a way that could cause the lung cancer? How would carrying a lighter cause the lung cancer? So you would at least want to have some explanation in here, right? That's what this arrow is about. If you can't think of any explanation, then it's kind of probably isn't that. It could be, but you wouldn't even be able to test it because you can't think of any explanation. So it's good to think of how they would do it. So a causal explanation. If you think they cause it, you don't have enough evidence now, but they might, okay? If the lighters are actually causing the cancer, we want to know that and tell people to quit carrying them. But how? So the question, how? Right? And the how is called a causal explanation or a causal link, right? How do they cause it? So that's called a causal link. A causation link, a causal explanation of the how. So you might want to think, and we're going to try to, the problem that you're going to do as an iClicker are going to be these problems right here, and we're going to have to say which one of these is a causal link. How would it do it? So that's one piece of the puzzle. And then the other is, but because it was not a randomized experiment, there could be a confounder. There probably is a confounder, and we want to try to identify it. We want to think, now we have to think, okay, what would a confounder be? It would be because those people chose themselves to carry the lighters or not. It would be a difference between that. First you have to think, what is causing them to choose one over, it's some difference between the people who choose the lighters and the people who don't. It has to be that. That's, difference between these groups. That's also a cause of lung cancer. So it might not be the lighters at all. That's called a confounder. It has to meet those two conditions. It has to be both a difference between the treatment and control group that's systematic, that random assignment would eliminate, a systematic difference. You have to think about difference between those two, and not only just a difference between them, but one that you suspect is a possible confounder of the lung cancer. Okay? And it can't just be some other cause of lung cancer. Because why can't it just be some other cause of lung cancer? Because then it could be another, there are many, many causes of lung cancer, but what we're trying to explain is this difference, why people who carry lighters are getting it more than people who don't carry lighters. So it has to also be a difference between those two. It can't be just some other difference that they're the same. It has to be a difference between the treatment and the control group, and also a possible cause of the response. All right, so here, let's just do, let's just do age here together, and then the rest of them I'm going to put, they're on the iClickers. So with age, what do you think it is? Lung cancer rates rise with age. This is the explanation. Now for all these questions, we are just interested in the logic, in having you develop the logic of causality. So please don't bring in outside information. That's not the problem. This is more like a logic problem or math problem. Knowing only this piece of information, that lung cancer rates rise with age. Okay, that's the difference between people who get cancer and people who don't. They're older, right? And don't bring any other outside information about what you know about the situation to it. These are for all these problems that you'll see. Because we're just trying to develop the logic of causality here. So what do you think that is? How many people do you see? Is it a confounder, first off? Well, it is linked to cancer, but is it, nowhere do I say it's a difference between people who carry lighters and people who don't. If I said that older people are also much more likely to carry lighters for some reason, then It could be really the age and not the lighters at all. It would be a very good confounder, but I didn't say that. And that's not, I don't even know if it's true or not, but it doesn't matter whether it's true. It's not in this problem, and it's not likely to be true either. So it's not a confounder. Is it a causal link? Does it explain how the lighters are causal? No. So it's really neither. And people do this all the time. They say, life is so complicated. It was an observational study. We can't determine, we can't pick out causation because there's all these possible causes and almost anything goes. Well, we're trying to be very logical here, and we're going to do statistics on this, and that's just not helpful. We want to know what we can change to whether to tell people to carry lighters or not, and we're trying to get at the root of that. Okay, so that's neither. So now let's go to the get out your eye clickers again. We're going to do the rest of them, and let's go to here, and okay, so let's start this one. So this is the genetics one. I'll just go to 30 seconds on these because we don't want to really waste time. Okay. All right, and now let's look at what you said. Okay, so this one is what? This is neither. It's the same exact thing as the age, and most of you got it. The same thing as the age. Okay, so let's go down. It's the age because it's genetics, because neither. Because genetics is a cause of lung cancer, but not a difference between the lighter carriers and the control group. It has to be both, okay? All right, let's do the next one. All right, I'll start it. Just 30 seconds. Okay, let's see what you did. Whoops. Okay, confounder, excellent. Most people said that. Great. So let's move on to the next. Let's see. Whoops. It's a confounder. Why? Because it satisfies both those conditions. It's a difference between people who carry lighters and people who don't. And also, smoking is a known cause of lung cancer. So more or less, the lighters are just a marker for somebody who smokes. And we can tell them to ditch the lighters and take up matches. They're going to get lung cancer at the same rate. So that's a confounder. Okay, it's mixing things up. Has nothing to do with the lighters. The true, lung cancer has nothing to do with lighters. Okay, so now we go to the next one, and we'll start this. Now, if it was true, remember, if it was. Okay, let's see, I did on this. Great. That is the causal link. You got that down. Great. That is how. If it's possible, it does. And that would be a possible causal mechanism. Great. Okay, let's do the next one. It explains how lighters could cause. It answers the question how. That's what a causal link is. All right, the next one. How about this? Radon. Okay, let's look at how you did here with radon. It's neither. Great. Now more people are getting it. Great. Radon is neither. Okay. It's because radon is a cause of lung cancer. That's true. But it doesn't explain, it's not a difference between the treatment and control groups. It doesn't explain why we're seeing people who carry lighters getting a higher rate. Okay, so now here's another one. Which of the following are possible confounders? Here, let's start this. Don't bring in outside information, just what I say here. Well, I guess you have to bring in some outside information, but. Okay. All right, let's see what you said. Yeah, all right. I say it's smoking cigars too. Maybe I should have, maybe you don't know about asbestos. Asbestos exposure, I probably should have given you, on an exam I would have told you more about it. This was just for in-class eye clicker. I would have had to tell you that it is a cause of lung cancer. You probably didn't know that. And smoking cigars, like cigarettes, causes cancer. Okay? So that's that, and I think we just have one more, and then we can get back to the, okay, so which of the following conditions have to be satisfied to be a confounder? All right, let's see what you said here. Good. This is it. That was the most common answer, both A and B. All right. Let's see. You have to, both have to be there to explain why the treatment appears to cause the response when it doesn't. Okay? It can't just be some other cause. All right, so let's go back to the document camera now and fill in what we said. Okay, so we said the genetics is neither. We understood that. The smoking cigarettes is the confounder right here. Smoking cigarettes because it leads to lung cancer, and also people who smoke are more likely to carry lighters than people who don't. So that's the confounder, and radon is neither. Whoops, look what I just did. My eyes are bad. I meant to circle the confounder here, and the lighter fluid, of course, was the causal link. It explained the lighter fluid was the causal link because it explained that the fumes are carcinogenic and cause, so breathing in that lighter fluid might cause lung cancer. All right, so let's move on. So now how do we stratify? Let's say we think it's cigarettes, okay? We think it's cigarettes. Let's show it's cigarettes. How can we show it's cigarettes? So what do we want to do? Instead of that blocking, we want to stratify, right? So we break the, yeah, sure.
Is there things that will mess up the results that aren't necessarily confounders?
Are there things that will mess up the result that aren't necessarily confounders? Good question. There are things that there are things that could better explain the results that aren't confounders, and there are bad practices that can mess up the results. You know, analyzing it the wrong way, of course, and everything. But assuming everything is done correctly. Yeah, confounders are the problem. They're going to make the result basically just unreliable. I mean, just wrong. They can be wrong. I mean, there's other things that could, like, for example, like in our data, like on comparing. So his question was, is there other things besides confounders that could make the results mess up the results? And I said, not really. There aren't. You could do the experiment wrong or something, or there could be things that don't fully explain, that you have to include that don't fully explain the results. In the context of the experiment we're doing now, like right now it looks like in Stat 100 and Stat 200, after we remove all the confounders, like it looks like there's no difference between the in-person and the online. But I'm not going to stop there. That doesn't mean that that's so for all the subgroups. It could be that for particular groups of people, for example, maybe non-native speakers, that online is better because they could listen over and over and over again to something. Or maybe people who are more social, maybe it has some effect on them to be around people while they're learning, etc. So what I'm trying to get at, or what you want to know, is there something called an interaction effect. So that doesn't mean that these overall results would be valid. These overall results would totally be valid after I remove the confounder, but that doesn't mean that it doesn't work differently for different subgroups. It could be, and that's what I really want to get at, so we could advise people. You're this type of group person, or in this category, you'd have a better chance in person. You're this type of category, And that's something else called an interaction effect, which doesn't mess up your results, it just gives you more information. Does that answer your question? I don't know.
I mean, it's like if you have genetic predisposition to lung cancer, it doesn't matter whether you carry it lighter or not. You might get cancer anyway.
Oh, you're asking something that I can really answer. So he's saying, why isn't these other causes of lung cancer, why aren't they important? Is that what you're saying? They're very important, but they're not important in telling whether lighters are the cause of cancer. They're very important causing, sure, we want to determine the other causes of cancer. For sure we do. We want to cure cancer, we want to figure out, of course they're important, but they're not important in this context to determine, what we're trying to determine here is whether lighters cause cancer. Thank you for clarifying. Yes?
So do you mean that when you were getting people for the experiment or taking observatory data, you would make sure to filter out those people if they knew they had genetic predispositions, or if they knew?
Okay, good question. So he's saying, if we are taking people for the study, are we going to filter out people who have high risk for cancer, other risks for cancer? We don't have to at all filter them out. We're just going to be, as long as they're evenly divided between the two groups. And so if we think that one group, we think the people who carry lighters are more likely to somehow have other predisposition, we thought there was a gene to carry lighters. There was also a gene linked to the gene to get cancer, then that would be a confounder. But we don't really care if there's differences between them, because there's not a reason to see these systematic. Yeah, go ahead.
For an example like that, would you stratify people with predisposition to cancer, or do you only stratify the confounder?
Okay, good question. So she says, okay, so do you stratify people who are going to be likely to get cancer anyways, regardless, in an observational study afterwards? So I don't think it would really make much difference if you did, because they'd probably be evenly distributed between the lighters and the non-lighters. So stratifying would say, okay, so people are very high risk for cancer who carry a lighter. Yeah, I suppose you could, just in case there is some link to it, but generally speaking, you're not going to find a big difference. That's a good question. There's another question too that I think you're playing around with, is here we're just talking about causation related to this particular group of people. We are not talking about extrapolating to other populations. That's something else. We are just talking about, in this particular group of people that we're looking at in these in the study, do we have a causal effect? If we really wanted to extrapolate to larger populations, we would have to randomly sample from a larger population. So that's another use of randomization. So here we're just looking at it as it relates to causation. Any other questions? Great. Excellent questions. I love that you're thinking about this. I mean, it's the most important question, right? We all want to find causes. So it's really good that you're asking these questions. Okay. So how are we going to do this? So how are we going to stratify? Okay, so we'll break the population into groups along the confounding factor. So we'll compare non-smokers who carry lighters. Maybe they carry them for other reasons. Maybe they smoke something else, like they carry them for, I don't know, they carry them for campfires or something, to non-smokers who don't carry lighters. And, to smokers who carry lighters. Excuse me. Non-smokers, you compare the lung cancer rate of those who carry the lighters to those who don't. So they're carrying a lighter for another reason. Moderate smokers, and then heavy smokers. All right, so you want to compare apples to apples. And basically, so it would look like this. In the beginning, you're going to have, okay, so what are we measuring here? We're measuring this like lung cancer rate here. That's our response right here. So that would be our lung cancer rate. And here's the treatment, and here's the control. And in this case, we're calling lighters the treatment, right? And not carrying lighters, the control. And on this lung cancer rate, we're seeing this. We see that the lighter people get a much higher rate of lung cancer. But now we break them down into these subgroups, like we'll say the non-smokers. You can do it as many groups as you want. The moderate, I'm just being simple here. And the heavy. Okay? And again, these are the lighters. These are the no lighters. Lighters, no lighters, lighters, no lighters. All right? That's what it looks like. And then if this happens, along some measure of how much they get lung cancer, well, yeah, the heavy smokers get a lot more lung cancer, but there's no difference between those who carry lighters and those who don't. So it's really the smoking, from this upward slope, you can see the smoking is causing the lung cancer, but within each group, there's no difference, so it's not the lighters. So thus the lighters are just a marker. Smoking for smoking. They're not causing cancer. So let's look at some of our own data before we, and you'll see how this plays out. So because here I'm doing all these theoretical examples, but let's just look at some of our own data. Okay, so here's a very clear-cut case of confounding in our observational data, survey 1 data. So we can go to the computer here. Well, why don't we just look at it first here. This is from a past semester, Stat 100. All right, so we have this correlation between how big people's feet are, so this is the shoe size, and how many pairs of shoes, shoe number. So this is how many pairs of shoes that they own. So you answered, we can look at, I don't know if we'll have time today, but we can look at your own R class data too, but this is from a past semester. And what is it saying? It's saying the bigger your foot, there's a negative correlation, there's a downhill slope, and that's a pretty strong downhill slope for observational data between the size of one's feet and how many shoes they own. So you might think, seeing this in observational data, does that mean that having a bigger foot, like bigger foot causes people to buy less shoes? So do big feet, somehow the bigger the foot, cause you to have less shoes? Buy less shoes. Why? You might think, okay, that's possible. You have big feet. Maybe they're less available. Maybe they charge like in country, it could be. You could have maybe big shoes are just hard to find, or if they charged by the material, and if the material is super expensive and the more material you put into a shoe, the higher they The more expensive they made it, so you'd have less shoes. So if big shoes were more expensive or less available, then that would explain it. Or more expensive, etc. There's possible ways, but more likely there's some confounder here. There's some confounder here, and the treatment you can think of as the size of the foot, and the response is how many shoes you buy. Okay, so treatment is so here's the bigger feet, big feet. We'll say compared to small feet, the bigger your foot, and the response is less shoes. I should probably make it symmetrical here, bigger feet. Instead of big feet, bigger feet, less shoes. Okay, so that's the deal. And what would be a confounder? To find a confounder, you have to find a difference between people who have big feet and small feet. You can think of this as like the treatment and the control. I'm just dividing it up into two categories, even though it's continuous. Some difference that also might be related to them buying less shoes. Right? You can't just think of some other cause of less shoes. You have to explain why it's related. Why this data was surprising. Why are we seeing this? Okay? And so can anybody think of what might be a possible confounder? Yes? Gender, absolutely. Because why? Males have big feet, and in the data, they also compare, and females have small feet, and males buy less shoes in this country. That doesn't mean it's culturally dependent, but it doesn't, but that's would be a possible confounder. So we could stratify. Let me show you on the computer before we stratify, and I'll show you what this looks like, the data. So let's go here, and let's go to the computer all right, so what do I want to do? Get out of here and go to our data program, and I can show it to you, and you can look at your own data too. It's kind of interesting. So let's go here. Okay, and so we'll go to our data program, and we can find this data. We'll choose, this is old Stat 100 data, so it's from Survey 1 from spring, let's see, Survey 1 spring 13. Okay, so here it is. So there was 1,046 variables, and if we look at this scatter plot, and we're comparing on the X variable, we have the shoe size, and here we have the shoe number. Okay, and so here we have the data, and you can see that there's a negative correlation. It's exactly what I put in the notebook. Now, let's stratify, okay? So what does that mean? So let's split the data into males and females. So we'll choose that split between males and females, and split the data, and look at this. It goes away completely, totally gone. If anything, it's slightly positive, it's totally gone. And you can see when you combine the data what's going on. Basically, the women, Stat 100 has predominantly women, they're colored in purple, and the males are colored in yellow here. And within each group, there's no correlation at all. It's just that women have both smaller feet and a lot of shoes. You can look at the statistics here, and you can see that the average shoe number for men is 6.8, and the average shoe for females is 20, 19.74. That's a huge difference. And the average shoe size for men is 10.6, and for women it's 8. So that's what's going on there. And we can just look at your data too. It's similar. We can do that next time. So that's what's going on here. So let's go to the document camera again. So that was a visual stratification, and you can see exactly what we did here. So what we did was we broke the data. Here's number of shoes right here. Number of shoes. And here we're saying, okay, females have more shoes. So this could be the smaller feet. And this is the bigger feet. That's what it looks like. But then when we break it down by the confounding factor, and we break it down into males and females, and compare within the male group, some of them have small feet, and some of them have bigger feet. But it doesn't matter within males, right? That disappears. So it's not the size of the foot, it's the gender. It's the same thing. So that is the idea. And you'll see this all the time. The visual explanation of it would be something like, an extreme version would be something like this. You have an X and you have a Y, right? And you might get a negative correlation here because you have one group here and one group there. I'm doing a real extreme version. And this causes the negative correlation. But within each group, that's bogus. That's bogus. That's confounded by group membership. So this is group A, this is group B. And within here, you could even have a positive correlation. That's what happens actually in your class in 200 right now. There'll be a negative overall, but inside each there's a slight positive. But all you see before you identify that confounder and realize, oh, if you're looking for causation, it is not X that's causing Y to go down like this. It's the placement. It's confounding by group membership. That is the visualization of it. And that's what we're going to try to get at through what you just saw was visual stratification. But what we're going to do is not break down over and over and over again into those smaller groups and keep breaking the scatter plot down. What we're going to do is show how we can do the same thing through modeling by adding, for example, gender as an independent variable. So instead of just having shoe size predicts how many, X being shoe size predicts Y, shoe number, we'll have X plus gender plus membership. We'll put two variables in, and then you'll see how it does a very similar thing. So that is the idea. So now I want you to read these. These are very philosophical. Read. I spent a lot of time writing it, and I think it's really important. 23 to 28. I'm not sure how much we'll get to in lecture, but read that on your own. But now you have enough to do the homework that's due Monday. Okay? Which covers also power as well. It's posted. So have a great weekend.